Welcome back, everybody. In the last video, we were working on the average rate of change and the difference quotient for a function, and I wanted to show you a graph on the computer that hopefully will illustrate that in some detail. So here I'm using decimals again. I have a graph of minus x squared plus 4 shown here in red, and also I've set up some formulas to show us the secant line passing through a point A and A plus H. And there's a slider here for A. Currently it's at negative 1.1 and my H is at 2. So here you can see that if I adjust the H, it changes the secant line. Right now the blue line doesn't look much like the red curve at all near this point, negative 1.1. But if I make the H just a little smaller, we make it a little smaller, we can see that it starts getting to be closer and closer to fitting the function over that interval. So let's make that a little bigger. So the smaller that h is, the better the function is going to fit. Here it's way off, here it's a whole lot better, okay? Additionally, we can see that if we change the value for a, then that changes where that point of approximation is. But at all points, the linear function is a pretty good approximator for the function that we had in the first place. Let me see if I could switch to our reciprocal function as well. All right, so here's our reciprocal function. I'm not sure if this may not be able to cope with that division. Let's see. There we go. I had a at 0, and of course it's not going to like a division by 0 there. So there was no blue line for a minute. All right, so here you can see that for any a that I choose that is negative, we're going to have a line that is negatively sloped. And then when a is positive, it looks positively sloped here. But if I make the h small and positive as it should be, then our function will be still decreasing, as I had said before. All right, so as long as our h is small and positive, we should have always a decreasing function. Again, the big takeaway here is that the linear function is a pretty good approximator for the curved function. So let's continue now with section 1.3. All right, so let's see if we can finish up section 1.3 here. We want to use a graph to determine where a function is increasing, decreasing, or constant. And I'd already used that terminology some, so we want to make sure that is we understand what that means. So when you're looking at a function trying to decide whether it's increasing or decreasing, we always want to look left to right. So for example, this function on the interval from a to b, it's increasing. If you look left to right, which is always how this is done, it looks like the graph is going up. And it's as simple as that. As you look left to right, is the graph going up? Then yes, it's increasing. Is the graph decreasing? Yes, it's decreasing on the interval from B to C because it's going down. And then on the interval from C to D, it's again increasing. A big thing to keep straight with this is that it's always as you're looking left to right, which is the direction that we read in, right? So we read left to right. So if you scan the function from left to right, you need to know, okay, well, is it increasing or decreasing? So try a little example here. We have the graph of 9 minus x squared, which is a parabola that opens downward. It has its vertex at the point 0, 9, and it has a couple of x-intercepts at negative 3, 0, and 3, 0. Okay, so taking a look at this one, if we wanted to know where it was increasing and decreasing, it's increasing on the interval from negative infinity to 0, and then decreasing afterwards from 0 to infinity. Okay, again, it's important to remember that you're looking at the function from left to right. If you were to draw this from left to right, you draw first up, then down, right? When you look at the graph, it's tempting to say, okay, well, it always goes down, right? The parabola is opening downward because that's where the arrows go, but that's not how this works. For increasing and decreasing, it's always as you look left to right. So if you look left to right, first it goes up, then it goes down. So it's increasing from negative infinity to 0 and decreasing from 0 to infinity. You'll also notice that when we report the intervals of increase and decrease, it's always an open interval. So I don't have a square bracket on the 0. We don't define increasing and decreasing at a point, okay, in this class. So it'll always be on an open interval, okay? So more examples. Okay, or here's another way of saying increasing and decreasing. This one is taken from a different book. This one is a little more formal looking. F is increasing on an interval I if f of x1 is less than f of x2 anytime you have points x1 and x2 in I and x1 is smaller. So what this says basically in symbols is if x1 is on the left, then its function value will be less than the other function value. F is decreasing if whenever x1 is less than x2 in I, we have f of x1 bigger than f of x2. So if x1 is on the left, then its function value is bigger. If you think about it, that makes sense. For an increasing function, the function value for the left point should be smaller than the one on the right. For a decreasing function, the function value should be bigger than for the point on the right. So spend a little time to take a look at this picture and make sure that you can match it up with the wording that goes above. Okay, it still will boil down to, as you look left to right, is the graph going up or down? But it's good to get used to that kind of formalism. Okay, so let's try a couple of examples. Here it says the graph of a function f is given. We're going to use the graph to estimate the domain and range of f. We can go ahead and do that. The intervals on which f is increasing and decreasing. So let's do that at least for, well, I've already done it for both of these. So save a little time, I guess. So for this first one, 31, it's increasing on the interval from -1 to 1. So when x is between -1 and 1, the graph is going up. When the x's are between 2 and 4, the graph is going up. And again, notice here we put this together with the union sign. It's decreasing on the interval from 1 to 2. So when x is between 1 and 2, the graph is going down. Increasing for this one, it's increasing on the interval from 0 to 1. So when the x is between 0 and 1, it's going up. If x is between -2 and 0, it's going down. And if it's between 1 and 3, it's going down. You'll notice when we specify intervals of increase and decrease that we're talking about the x values, right? So here, let's use this one. When I'm talking about the function, this function increasing on the interval from -1 to 1, and then from 2 to 4, you'll notice that I never mentioned this 2 and 3 because it doesn't matter. We're not talking about the y values here. We're talking about the x values where it's going up, the x values where it's going up over here, and then the x values where it's going down are between 1 and 2. We didn't mention the fact that it's decreasing y values, anything about the -1 and the 3. It's all about the x values. All right, so I had done the increasing and decreasing already. I should give the domain and range though, because that was part of the directions. So the domain is the x's, so that will be -1 to 4. For the first one, the range is -1 to 3. And then for the second one, number 32 here, the domain is -2 to 3. And then the range is -2 to 3 also. That's interesting. Okay. All right, so that has been about increasing and decreasing. The next part has to do also with describing characteristics of graphs, and has to do with maximum and minimum values. So this part is from our textbook, so I wanted to include in here how our textbook describes increasing and decreasing. Instead of saying x1 and x2 for this, they say, okay, well, it's increasing if f of b is bigger than f of a, and b is bigger than a. It's decreasing if f of b is smaller than f of a, and b is bigger than a. So you might want to draw a picture for this. Let me start you with the picture. Try to think about what it means to you to have an increasing function. So that function is increasing, and both of these say b is bigger than a. So there's A and B like that. B is bigger than A. How is f of B related to f of A? Which one's bigger? Okay. If it's increasing, f of B will be bigger. If it is decreasing, f of A will be bigger. All right, so you can contrast that to the other kind of description of increasing and decreasing that we have seen. All right, so the next thing is we want to talk about maximum and minimum points. So here, that's basically a maximum is going to be a high point on the graph. So if you have a graph like this, where there are high points on the graph will be maximum points, and where there might be low points on the graph will be minimum points. Okay, there's a symbolism for this, of course. A function f has a local maximum at a point B, that will be an x value, in an open interval from A to C, so all this is described on open intervals, if f of B is bigger than f of x for all the x's in the interval. That's a mouthful, so you have to read through that more than one time, and that's fine. F has a local minimum point B in the interval A to C, if f of b is smaller than f of x for every point x. So like I said, that's a lot of symbols. So we'll try to make that pretty understandable with an example. All right, so here it says the graph of a function is given. We're going to use the graph to estimate the following. We want the maximum minimum values and the value at which each occurs. We'll also give the intervals of increase and decrease. Maybe we'll just do 43 here. So first of all, maximum and minimum values. So I'm going to go with the maximum first. So it should be pretty clear that it has a maximum of 2 at x equals 0. Okay. So to kind of compare that to what the wording says, okay, in this written definition for a maximum, a function f has a local maximum at a point B if f of b is bigger than the f of x's in the interval for every point x in the interval. So going back to the graph, what that says basically is this f of x you're seeing here in purple, is that bigger than all the other f of x's nearby? Yes, that's what that inequality says, is that this f of x is, that function value is bigger than the other function values nearby. So it turns out that that's the only maximum there is. There are 2 local minimum values though. There is a minimum of -1 at x equal -2. And then also there is a minimum of 0 at x equal to 2. Okay, so I guess I should recall that here. So there was a maximum of 2 at x equals 0 and minimum of -1, x equal -2, and 0 at x equal 2. Okay, so then intervals of increase and decrease. So let's get that there next. So where is this thing decreasing? It's decreasing from -infinity to -2. Okay, as we look left to right, as x goes from -infinity to -2, it's coming down. And then it goes up for a while. And then it'll come down again as x increases from 0 to 2. And then basically it's increasing everywhere else. It's increasing as x varies from -2 to 0. And then it'll be increasing again as x increases from 2 to infinity. So make sure that you can look at the graph and kind of see how that's working. As we look left to right, you can see where the graph is going up, it's increasing, and where it's going down, it's decreasing. And if you think about it, how that fits with the maximum and minimum values should make sense. If you have a minimum, as you do right over here, if you have a minimum, the graph should be going down first and up afterwards. If you have a maximum, the graph should be going up first and down afterwards. Okay, so again, with the minimum here, the graph has to decrease first and increase afterwards. Okay, so I'll leave it for you to try this number 46. I'll help you with the maximums. This one is going to have 2 maximums and 2 minimums. And notice that it is alternating between increasing, decreasing, increasing, decreasing, and so forth. Okay, so try that one, number 46, and let me know if you have any questions on it. All right, so the last example had to do with relative or local extreme values, maximum and minimums. There's, let me go back. There's different terminology that you will see with this. Our book refers to local maximum and minimum values. You may also see the words relative. If you look on Google or in other books or other YouTube videos or something, you may see them refer to relative maximum and minimum values. And what that means is basically the maximum and minimum values right around a particular point of interest. In this next part, we're looking at the absolute extreme values, which would be the absolute maximum or minimum values. The other way that you may hear this referred to is global. Okay. All right. So the difference between this is that the absolute ones are for the whole function over its whole domain, whereas local, if you think about what the word local means, that means right around a particular neighborhood. Okay. So maybe you are the tallest person in the room, right where you are right now, but maybe you're not the tallest person in your house or in the whole world. Okay, but just in a particular area or neighborhood, you may have a maximum or minimum value. For absolute or global, that means over the whole domain. Okay, so that's a big difference here. The function f has a maximum at c if f of c is bigger than all the other f of x's in the whole domain of f. And then if f of d is smaller than all the other f of x's in the whole domain of f, then it is a minimum value. All right, so let's try this example, which is taken from the book. So here it says, if the complete graph of the function is shown, estimate the intervals where the function is increasing or decreasing. So let's try increasing and decreasing first. So it looks like it's increasing from -8 to about -3.5. So let's go with increasing between -8 and -3.5. And then it also looks like it's increasing between about 3 and about 7. Let's say 3 and 7. Let me double check that first one again. That looks more like it was closer to -3 for that first one, -8 to -3. That would be where it's increasing. And then it's decreasing between -3 and +3. Okay, so then absolute maximum and minimum. So the absolute maximum is going to be 150 at x equals 7. The absolute minimum looks like it will be about -225 at x equal -7. Okay, because those are the highest points on the whole graph. The question here doesn't ask about the local or relative extreme values, but let's go ahead and put those on anyways. It looks like there is a relative maximum at x equal -3, and it looks like it's a value of 50 at x equal -3. By the way, you want to make sure that you're distinguishing between the function value and where it occurs. On this one, if I asked you, what is the absolute maximum for the function? Is the absolute max 7? No, the absolute max is not 7. The absolute max is 150. It happens to occur when x is 7. Okay, but the maximum value itself is 150. In a similar way here, the relative maximum is 50. It occurs at x equals -3. Okay, the relative minimum, it looks like it's -50 at x equals 3. Okay, so absolute maximum and minimums are the highest and low points over the whole graph. Relative maximum and minimum points are the highest and low points, not necessarily of the whole graph. It turns out that the absolute extrema are also considered relative. So let me re-say that. If you think about all the different extreme values you can have, maximums and minimums, okay, there's relative ones. Out of those, a subset are the absolute ones. Okay, in other words, the absolute maximum and minimum are also relative maximum and minimum values. Okay, so that finally takes us, I think, to the end of section 1.3. Let me know if you have any questions on any part of this, and then get started on that assignment for it, and then also have a great day.